This conference will now be recorded.
So we'll start off with a quick recap, like what we have discussed in the last webinar, because basic understanding of container and Docker, etc., is very much required for understanding the Kubernetes concept or container orchestration concepts. So yeah, then followed by we'll talk high-level architecture and how to different ways to run Kubernetes, like for development purpose as well as for production. Then we'll test base a little bit of networking and security, the ways to persist data, and how to monitor the cluster, as well as how to troubleshoot using the logs. And we may test base, like if the time permits, some theoretical discussion around service mesh. All right, so. There are a few slides which we've been through in the last webinar, so that's going to be a little redundancy, but give it like 5 minutes. I'll cover it quickly, and then we'll jump to Kubernetes. To set the context, right, the container technology. So this is what we have discussed last time, right? So we had the bare metal where we have operating system and application installed within it. Then we introduced virtualization where we can split that particular resource into smaller pieces. And in this VM, again, we have the operating system, and then we install our applications. So from there, the transition was containers, right? So where we have the operating system, which supports the container runtime, and then we run the application as the container which a shared operating system kernel. So why would we go with something like container? The main thing, right? So it is like if you have an application, previously we have to make sure that wherever you run the application should have the required dependencies installed, and let's say the web server configuration or security, etc. So in container, you can actually build the complete application with the dependencies and configuration like a package, like an image, and then if it works in your dev environment, it is going to work in all the upstream environment, because pretty much you're running the whole isolated the system, right? So you have the dependencies and everything inbuilt. So we'll just touch base and see like how it actually function. So in the Linux kernel, in Linux architecture, we have this concept like user space and kernel space, right? So in containers, containers use the same kernel space or as the host machine, right? So you have a host machine, and on top of it, we have the container runtime, and then individual containers share the same kernel space. So what is different is just the user space. So we can have different different containers with different user side libraries. And then there are these Linux kernel features which it uses to build the container the technology. So it is not using any of the low level the virtualization. It is not a VM, so we cannot compare a container with a VM. So container is a process just like the process running in the host system, and it is not a VM. So having said that, that process get isolation in different levels. So the process is isolated in terms of its file system views, and we have the concept called namespaces and C groups, and other features like security network which enable us to do that. So we'll quickly touch base these points. To start off with the file system, right? So these are the OS features which enables the file system, like in containers, the device mapper, BTFS, and AUFS, and overlay. So there are two main concepts. So one is the union file system. So when you say AUFS or BTRFS, they are like union file system. What is a union file system? So you can actually keep multiple images on top of another, map on top of another, and then you can have a union of all this file system. Like for example, I can have a, let's say, base image, which is operating system, user side libraries, and on top of it I can install a web server and then do some configuration. on top of it, I can have my application copied, right? So we have now 3 layers formed. So each of them are independent layers, but then union file system allow us to have a union view of the whole thing. So that's what the main concept behind the container file system. And next important thing is the copy and write storage. So when you run a container, the image is immutable, right? So you won't make a change to image. So what happens is the individual container will have a writable file system on top of it. Meaning, let's assume I'm running Nginx, like 5 different instances of Nginx is in 5 different containers, right? So we will have only one container base image, right? So and all these 5 instances will be pointing to the same base image, but all these instances will have a writable container file system, a very thin writable container file system. And what is it used for? Let's assume within your application we want to make some changes to the underlying image. So then it copies that particular binary and put it to the writable container file system and then modify it. So it does not modify the underlying image. So image is immutable. So this actually saved a lot of space, right? So you have many applications, many containers, and you don't have to replicate the complete image many times. Rather, you have single image and everyone is pointing to the same image. So then the namespace. What is a namespace? So we have, there are 2 diagrams here. On the left side, you can think about the left side diagram as how host system would look like. Let's say you don't have any container. So this is how host system would look like. You have a single next namespace, single IPC, single user, single PID. So there are different namespaces. You have single namespaces. So a namespace will give you a kind of logical isolation for a process. Like for example, a process in namespace A can see only the other process in this given namespace. So it won't be able to see the other process in the namespace B, for example. So if your host machine is partitioned to different namespaces, so that is nothing but the containers, right? Now that we know, how to partition and give a kind of isolation within the host machine in terms of the IP stack, in terms of network, in terms of the file system, right? Now the next thing is like how do you control the resources? For example, our host machine does not have unlimited CPU or unlimited memory, but then there should be a mechanism to allocate a given memory or given the CPU to all these namespaces, right? So that's where the control groups come into play. So we have different control groups like for CPU, CPU set, memory, block IO, etc. So we'll be able to allocate those resources to a specific namespace. So and lastly, the security and networking. There are different the low-level kernel features which enable the security and networking. So capability, security and enhanced Linux kernel, and the seccom, the module. But what we will see like in the later part of the section is the networking, where we'll talk about the virtual Ethernet and bridge and how they talk. So basically, these are the Linux features which enable the container technology. So Docker. So we have seen it during the last webinar. On a high level, we have the Docker client, the host, and registry, right? So the Docker client is a place where you run your CLI. So you have the Docker runtime running in a host, right? So and all your images, right, is placed in the registry. For example, if you're building an application, you'll have a Docker file using which you build an image and you push that particular file, image to the registry, right? And also the same file will be cached in the the Docker host. Okay. Now when you run it in the Docker host, it will create a new container, right? And then you have the port mapping, etc. So on a high level, we have the Docker client which interact with the Docker host over REST. It has the REST endpoints, right? And then Docker host has the Docker daemon and where you are running the container, and it also caches the images so that each time whenever you are trying to download something, it does not have to go to the registry, right? And we have seen this during the last webinar. So these are the main Docker objects. You have the images using which you create a container. So container is nothing but a runnable instance of an image, and then we have services. So in this diagram, if you can relate the way we do, like in old-fashioned way. Like for example, you have a let's say the operating system image, right? That image we use for creating an instance, a virtual server, and onto that virtual server, when it's running, you can mount volumes. So logically, we can kind of see the same thing here, right? So you have a file which describe the image using which you build the image, right? And then you can run the image, and on top, I mean, to that image, this is nothing but a container, and the containers you can network, and then you can mount volume to the network for storing something. And we have seen the different commands, and what all things we can do within the image and container. So we have different statuses, mainly created, stop, running, and pause. And then in each status, you can run different set of commands which will transition it to a different status. And one last slide before we jump into Kubernetes, the Docker Swarm. Uh, so mostly we have discussed about how to run the Docker containers in a single host, right? Not like in a multiple nodes. So in production environment, obviously we will have multiple nodes for redundancy and for scaling, etc. So how do we, execute these containers across different nodes? So Docker has inbuilt functionality called Docker Swarm. So with one command line, we can actually spin up the complete. I mean, we can actually convert the node to the master, and also you can make other nodes join using token. On a high level, it has like manager node. Sure. So yeah, so on a high level, we have the manager node and the worker node, right? So whenever you create something, so you give the instruction to the manager node, which actually make that particular, I mean, schedule the container in a worker node and execute it, right? And then you have this distributed state store. If you have multi-master, it will be spread across multiple nodes. So this is like, I mean, Docker Swarm does give basic functionality, or for running most of the small scale applications in production. But even like larger scale, I mean, it is okay to run Docker Swarm, but it is not that feature rich like Kubernetes. So this is what we discussed during the last webinar. Now let's quickly jump into Kubernetes. So what is Kubernetes, right? So it is a container orchestration technology. So it was developed by Google. It was not called Kubernetes initially. So that it was their in internal project. They've been using it for running their production workload for decades. Later on, they open sourced it. So yeah, so the project was born, like Kubernetes as a project was born like 2014, but it was pre-existed like decades back. So you can consider Kubernetes as a container platform. You can, I mean, a platform using which you can run, the multiple containers across different nodes which are connected, and a microservices platform. And there are, of course, multiple, the applications built on top of Kubernetes, things like OpenShift, etc., which is like purely a microservice kind of platform where you can run your containerized applications, and it is even part of the complete SDLC. And it is also a portable cloud platform. So there are situations, and in these kind of scenarios are kind of increasing. Like you will have multiple multiple infrastructure. So one part of your infrastructure is running in, let's say, a Google Cloud, and another is GCP, or another is running in, let's say AWS. Or I mean, this is a natural scenario where you have part of your workload in on-premises data center, and part you migrated to, let's say one of the cloud vendor. So basically, Kubernetes you can run in all of this. It's actually cloud native, meaning you can run in multiple cloud. Also, you can run in the typical, virtualized on-premises infrastructure, and everything can be connected. So that's the beauty of Kubernetes. So how does it look like? So, like you have seen the Docker architecture, it kind of similar, right? But it's not the same, but it kind of similar. So you have this master node and you have worker node. You can have multi-master as well. And there are different components in the master node. To start with, you have the Kube API server. So there are multiple ways in which you can interact with your Kube API server. So Kube API server hosts the REST endpoints, right? So you can talk to Kube API using kubectl or kubectl. It's a CLI which talks to the REST API, and also there's a UI using which you can talk to the Kube API server. Now there is controller manager, which actually manages multiple control loops, which we'll talk about in the next slide. And a queue scheduler will actually determine where to run your the worker, the workload. And the cluster data is stored in etcd, so it's a key value pairs store. And each worker node has kubelet and kubeproxy and optional add-on DNS, and most of the times, or almost all the time, we use DNS. So kubelet, kubelets talk to the container runtime and then run the container, or you can say pod, because it's slightly different, like in Kubernetes, right? So pod is like a little bit abstraction on top of a container. So, and API server talks to kubelet and kubeproxy, and kubeproxy main functionality is to set up the services, and we'll discuss what a service is in Kubernetes in upcoming slides. And obviously we have DNS. So DNS install on all the nodes, and it's a cluster-wide name resolution. So each port names can be resolved within the cluster, or each service name rather can resolve across the cluster. So in a typical use case, the user create a YAML resource. So everything, all the resources in Kubernetes can be represented in YAML. So user create a YAML file representing that particular resource, and then execute some command using kubectl. So kubectl convert that YAML resource to JSON and make an API call to the Kube API server. So what the resource definition file contain is the desired state of something. Like for example, I want to run this container, 2 copies of this container, right? So that's a desired state. So that will be persisted in etcd, and then the scheduler, controller manager, the kubelet, and kubeproxy, all of these work together to make sure that that's happening. So whatever you mentioned, like in the YAML configuration, is actually applied, and the desired state is current state, meaning like it will make the current state as a desired state. So like we discussed, we have the master components, node components, and some add-ons. So I think we test base this. So in Kube Controller Manager, this can be confusing sometimes because there are multiple controllers. So there are multiple logical controllers, but then all the controllers are part of the same binary. So basically, when you run as a service, it's actually just one, right? So but then there are lots of logical controller. A control is nothing but a control loop, constantly checking to realize something, right? So like for example, a controller for replica set, making sure that, let's say, 2 copy of the pod is always running, right? and controller for setting up something called ingress. I mean, there are controller for many things, so there are multiple controllers. So basically the idea is there are multiple controllers, everything is bundled in a single binary. So as a process it run as a controller manager. And then we think we discussed this. So the container runtime, so by default people use Docker, but there are other Docker container runtime like Rocket and Containerd, etc. So which also work with Kubernetes. So it's just not Docker. And add-ons, like I said, by default when you set up DNS is not inbuilt. So there's CoreOS DNS which we usually install, and also there's a nice looking dashboard which will tell you like how your cluster look like all the resources running in the cluster. So that is also an add-on. So now that we have a basic idea of what Kubernetes is, like how do we set up, right? How do we set up the Kubernetes cluster? So if you want to just, I mean, if you're very new to Kubernetes, you just want to play around, the easiest way to set up is Minikube. So that's what people say, but I actually got started with the corps. So I'll tell you the difference. So Minikube is nothing but, something that you can install in a single node VM. So let's say I'm currently using Windows machine, right? So in the previous webinar we have seen how we can install Docker. So you have the Docker tools for Windows which spin up a Linux VM, right, within the Hyper-V or VirtualBox, and then the CLI talks to this particular VM of the REST interface, and same thing happens of the Minikube. So the master and the worker node, everything together. So everything is like in the same node, and you have the kubectl or kubectl we install in your local machine, which talks to this interface. So sometimes it can be painful, and sometimes it can be very slow, right? Running the Minikube. So that's my experience. Also, like there are multiple documentation which you can refer how to set up Minikube. On a high level, it is a very straightforward, steps, but sometimes you can get stuck based on your operating system version, the hardware requirements, etc. So, but that is like very difficult to take you through the steps because it purely depends on what kind of operating system, what kind of laptop or desktop you're using. So, so that's the easiest way you can get started. So, how would it look like? I don't know whether the Minikube crashed, but still I'll just. So kubectl is the CLI, like you have the Docker CLI, which used for talking to the API server. So like I mentioned, in my machine particularly, it's kind of very slow. So now we can see some response, right? So all you need to do, like once you install everything, you'll say like Minikube start. And sometimes you may have to give the the VM driver. So based on whether you're using Hyper-V or VirtualBox, but otherwise it's almost like Minikube start. Then you'll have this environment up and running. Then you can start using kubectl to interact with your cluster. So here, what it says is you have two services. One is Kubernetes and Proxy Nginx. So this is which I've run, right? So we'll talk about those things later, once we cover what is a pod and what service, etc. So that's about the single node Kubernetes, which you can run locally, right? So that's Minikube. So these are the other two ways: kubeadmin or kubeadm and kops. So kubeadm was initially there. So this is built kind of replicate the Docker Swarm functionality. So Docker have this nice cool thing called Docker Swarm init. If you just run Docker Swarm init, then that particular node becomes the master, and it will give you a token using which you can make other nodes join the cluster. So it's a very easy way to kind of set up the the cluster. So so Kubernetes kind of replicate the same thing using kubeadm. So using kubeadm, we can, it's again command line using which you can set up the cluster. When you say set up the cluster, you can initialize a master node, and then it will give you a token. Using that token, you can join other nodes to the cluster. So I've actually documented the steps, like in you can see the steps in multiple portals as well as in official Kubernetes documents. But also I have my Git repository where you can see the steps which you can just execute and build a Kubernetes cluster. Now kops or Kubernetes operations, right? So this is something people use for kind of production quality, building production quality clustering specifically to AWS. So they have beta support for Google Cloud, but specifically it is for AWS. So the main difference between kops and kubeadmin is kops will set up the underlying infrastructure, meaning kubeadmin, if you want to run, you need to manually provision your nodes. Let's say I need 3 nodes, one for the master and 2 for the worker. So I need to provision those nodes and set up the network, etc. But then for the kops, it actually set up the complete infrastructure for you, and that is also customizable. There are lots of parameters that you can pass, as well as some of them can be described like in a YAML declarative fashion. So let me show you how the kops output will look like, right? So this is a cluster which I've created like in AWS using kops, right? So I have a master node, I have a the worker node, and the first one I just spin up just to execute this command instead of executing the same commands from my the desktop. And it also the setup, the security groups required, load balancers, etc., etc. So it does everything automatically, right? And then you can straight away put into it, and then start interacting. So cubes. So this is the jump host, which you can see here, which is in the same network. So I can where I'm having the CLI using which I interact with the cluster. Let's say I don't have anything running, so I'll just say the namespace cube system. So you'll see some system. So these are the pods and service and deployment, etc., which is already running when you set up a cluster. So like we have seen the diagram, we have something called DNS. Then forget the Elasticsearch, that's something I've configured after that for logging. Then etcd is the database, and then Kube API server, DNS proxy, scheduler. So all of these are set up, right? So some of them will be in the master, and some of them will be like in the worker node, right? So we'll see what all these are. All right, so these are the 3 different ways to set up your cluster. So most likely you can start off with the Minikube, where you don't have to have a cloud account and then pay. I mean, it's not actually free. So basically, when you set up a master has to be medium, and it's not T2 micro. So T2 micro covers as part of the free tier, and medium does not. And along with that, there are a few other things, like for example, the load balancer for the proxy server, etc. So even load balancers are charged, right? They are not free. So when you use kops to spin up a cluster in Kubernetes, sorry, in AWS, it's not free. You will end up paying some, a small amount, let's say $10 for some 3 days. So let's start off with the basic concept, like what makes Kubernetes, right? The building blocks of Kubernetes, or different the resources in Kubernetes. So start off with pods, right? So what is a pod? So in Docker and Docker Swarm, we have seen what is a container, right? So pod is the smallest the unit that you can run in Kubernetes, and a pod can contain one or more containers. So a pod can contain one or more containers which shares the same network, IPC, user, and PID namespace. So you have seen even PID. So which means the pods, the containers which is running within the pod shares the same IP and same the process namespace. Meaning if I'm running a process A in a container 1 and process B in container B, both can see each other, right? Because the process namespace also shared. So like in the diagram, you can see the UTS and mount. So mount is the view of file system. So only the view of file system is different, but others are kind of shared. So you can put multiple containers within a pod, and also we can have the persistent volume. So we'll talk about volume later. So pod is a group of containers, right? So in most of the scenarios, you will not run multiple containers within a pod. It is going to be one-to-one. So if you want to deploy a microservice, it is going to be just one-to-one. But there are scenarios where you end up creating multiple containers. Like if you want to inject a sidecar proxy, so we'll discuss that approach when we talk about service mesh. But otherwise, you will have one pod having one container, right? So pod represent a running process on your cluster. Pods are not visible outside the cluster. So all the container will have its own IP address, right? So you won't be able to talk to those pods from outside. So when you say container will have its own IP address, since the pod share containers share the same network namespace. Basically, the pod has the IP address, right? Because there are no two IP addresses like within the pod. So share same network namespace. A pod can contain multiple containers and or volume. So how do you define a pod? So in Kubernetes, you declare or describe the resources in YAML, right? And then you pass in the YAML to the API server. Not exactly. You convert that to JSON and then pass to the API server, which will then try to run it, in the sense try to realize that particular state, right? So this is how you define a pod, right? So most of the resources have all the resources will have API version and kind. The kind is like nothing but what is the type of resource. In this case, we want to define a pod, right? And metadata, the additional data that you pass in for any resources. So metadata also common to any of the resources. And then you have the actual specification where you can see the containers and where it's using name of the container is Ubuntu and image to use is Ubuntu trustee and some other arguments that you can pass to the containers. But there is one more important thing which I have not mentioned here, which is the label. So we'll talk about that in the next slide. So on a high level, this is how you define a pod, right? So a YAML file, you have the kind as a pod, and then you have the spec, and pod contain multiple containers. If you see that containers, it's an array, right? It's not one, so you can have one or more containers. So the dash signifies array, like in YAML. So in the right side, you can see the diagram, right? So you have one pod, two pods, each containing one container, each have its own IP address. Let's assume it has some port for the container, right? So now, how does the user, talk to that particular container, right? So it's not possible. So as we saw in the previous slide, pods are not visible outside the cluster, right? So that's where the service come into play. So we will go to service, and then after that we'll try creating a pod and service. So what is a service? So again, if you look at how to define a service, it's a similar syntax, right? So you have the kind, the type of resources service, then you have the API version, the metadata, then specification, correct? Specification, that's where the actual thing you mentioned. So one important thing is the selector. So I mentioned about there is one item which is missing in the first diagram, which is the first YAML, which is the label, right? So the way it works is like this, right? So the pod can have multiple labels. A label can be any key value pair, like for example, environment, production, or something like that. You can add anything, or the name of the microservice, right? So what service does is service will find all the port having that particular label and then send the traffic to those port. For example, I have a service called, uh, let's say products, right? So when you run in production, it will have multiple copies, right? So there will be multiple port for the same service, right? Because I won't have just one port. So it's either for scaling out, or maybe for redundancy, right? So we have multiple ports. So the port also can die, in the sense, like, for example, if there is issue with the application and it is having memory leak and a port crash, right, then it will create a new container, a new port, right? So it can be replaced, right? And another scenario would be like, let's say I want to scale it, in the sense I'm getting more traffic, so I want to add few more instances. So now there are not much traffic, then you'll reduce it, right? So basically what I'm trying to say is, like, the port IP address is not stable. Port can die. Ports are, in an analogy, they compare ports as cattle and the service as the pets. So cattle, right? So which means, like, it can actually be replaced by something else, right? Now, if you look at the YAML file, you can see the selector. So selector have app and nginx. So if I want to send traffic to list of ports which is running nginx, then all the nginx YAML or nginx resource should have label named app nginx. So that's how we find out, right? And also there is a concept called name port. You can see the port. It can open multiple port. Again, it's an array. You can see the dash symbol and HTTP and port 80. So 80 is the inbound port, and it will translate to the target port as 80. So that 80 is nothing but the port in the container or port. So let's quickly check a sample app. So this is a standard sample app, like in the Kubernetes, to guestbook app. So basically, so we did, yeah. I think we'll come back to this, after going through deployment and service. So deployment. So now we discussed about the port, like in a high level, sorry, service in a high level. Now, how do we get into the service, right? So there are different types of services. So by default, all the services type is like cluster IP, right? So if we go here, you see the type as load balancer, right? So if you don't mention any type, or if you explicitly mention the type as cluster IP, so it'll become the cluster IP. So even if you don't, for example, if you have a service which you don't have to expose outside, then you can make it cluster IP. So only the services within the cluster will be able to talk to it. So a cluster IP, meaning it's a virtual IP which is visible within the cluster, and it's not tied to any network interface or something. It's a it's a different technique. So we can think about, like, if you have a service which you mention as a cluster IP, that service is available only within the cluster, right? And the second thing is node port. So node port, if you mention a service type as a node port, and you mention a port number, so port number has to be above 30,000 and between 30,000 and 30,000, 32,000 or something. So there is a range. That range, like, it dynamically assign a port number. So when you say node port, right? So what technically we can do is, like, let's say we have a single node, right? So here we have two worker nodes. Let's assume we have a single node. So that service will be available, like, in that particular node, meaning, like, I can go to the node IP address dot, colon, the port number, the dynamic allocate port number, then I'll be able to access the service, right? So when you select as a node port, what Kubernetes does is it will open the same port for that particular service in the host in all the worker nodes, not just one. So if you have like 10 worker nodes, all the 10 worker nodes you will have that particular port open for that particular service. So why is doing like that? Because there's no guarantee that where your pod is running. It could be running in multiple nodes or a single node. So wherever you hit, you should be able to reach the particular pod. So to that purpose, it open this pod in the host machine in all of those nodes. So then third type is load balancer. So load balancer, like in the picture, you can see you have a load balancer which is balancing between like these two nodes, traffic to these two nodes. So load balancer support is available only if you want to, if you deploy your, Kubernetes in any of the cloud. So that's a cloud specific implementation. So based on different cloud vendor, you'll have different types of load balancer allocated. But the main problem with this approach is, for each service, you'll have a separate load balancer, and load balancers are not free. So if you have like, let's say 100 microservices, then you'll have 100 load balancers, right? So that's how it works. And in the node pod, node pod, we don't use it, right? So we won't use node pod approach in production. So it's only for, if you want to test it or, something like that, but you'll never use node pod approach also in production. And load balancer is relatively, usable, but, even since it has to be like one load balancer to one service relationship, we tend not to use it, right? Then the fourth option or mostly used option is ingress. So ingress to understand is slightly difficult. So it's about you having one, a proxy, and based on some route rule, like for example, /API goes to some set of service, and one service, and let's say products go to another service. So you define those rules, and like this each URL segment and where it should route to, like which service and pod. So the main advantage being you can have a single ingress proxy, which can be used for facing your complete services. You don't have to create multiple load balancers. Rather, it's just one which will route the traffic to the complete cluster. So we will see some of this in some time. So before jumping on to demo, let's see two more concepts. First one being replica sets. Now we discussed about running a pod, right? We can create a pod resource, YAML, artifact, and then create a pod. Now in production, and again, like as we mentioned, pod can crash and can be replaced by another one, right? And also, if you want to automatically scale it, you should be able to add new pod, etc., right? So no one create just the pod artifact and manage it, directly. Rather, there are multiple level of abstractions, and one of the abstraction is replica set. So what replica set does is, let's say I want to run 2 copies of a pod, right? 2 copies of my service. So I'll define a replica set, and in this particular example that you can see that replicas is 3, right? So like you can see the kind as replica set, and then you are defining that I want to create 3 copies, and then you can pretty much see the container specification, right? And again, you have the labels. So labels are what help to find those particular target ports, right? Now you have the the container. So basically, the replica set will make sure that you always have 2 pods running or 3 pods running. So if one crashes, it automatically replaces it by another. So the desert state will be always met. The desert state will be always met if you do the replica set, and you don't have to manually manage it, right? And there is one more abstraction which is the most used now, is called deployments. So now if you look at the structure, it's almost like if you replace the replica set with deployment, then that's what you see the deployment. So within the deployment, you can define how many replicas you need, and the main beauty of deployment is we can enable like blue-green deployments. Like for example, I have version 1 running. It has 2 replicas. Now I'm going and updating the the container image like in the deployment file and update again. Then it'll automatically switch the traffic to the new version and it'll set the replica set, all replica set to 0, right? And let's assume like there is a production issue immediately, and then you want to switch it back, then you can actually switch it back to the previous version. It keep the history, but anyway, I mean, switching back using deployment is not a good option, but still, I mean, you can. I mean, it's doable. So basically, it's a little more, higher level entity or higher level abstraction on top of replica sets, right? Now let's look at some of this application. Okay, so this sample app have a front end and back end is powered by Redis. The front end is like in PHP, right? So you can see that the front end has a deployment and a service, right? So if you go to the deployment, you can see the kind of deployment, then specification. You can see the selector uh, for that particular deployment, and most importantly, the replica set is 3, and then container, and the pod has a label. So this is the label which the service used to find the pods. Now, if you go to the service, you can see the selector as app is equal to book, tire is equal to front end, and you can do the same thing here under labels. So in the service, it's called selector, and here is label, right? Um, yeah, and in the Redis, this is the deployment, which actually spin up the ports, and this is the service, right? Now let's actually apply this particular thing and then see how it works. Now AWS, the cluster setup in AWS. Okay, where is that samples? Okay, finally we are here. So what is the YAML file, which you can see here for creating these resources. So I think all-in-one has one resource. Yeah, so we have these 3 YAML files. So how do you create this, right? Uh, so kubectl, now I want to apply a YAML file, right? So first we create the Redis master. So first we need to create the pod and then the service, but even otherwise it will not create an issue. Redis master deployment. Okay, created Redis master service, created. Then we have Redis slave deployment and slave service. So what we have just done is we have created the pods, which is part of the deployment, like we have seen in the slides, and the service. Service will be pointing to those deployments. I mean, pointing to the pods defined in the deployment, right? So that is done for the Redis, and now we have a front-end service. Okay, now we check the running ports. You can see get ports or get PO will be good enough. So you can see that we are running 3 copies of front end uh, because we have in the deployment mentioned I want 3 replica, right? 3 copies of the front end, and then we have a master and 2 slave. So if you look at the slave deployment, there are 2 replicas, and if you look at the master, you have only 1 replica, right? Now, if you want to see the service, that SVC will do. So you can see you have a front-end service created, and forget the Kubernetes, it's a inbuilt and Redis master and Redis slave. Now, if you want to see the details of the service, right? So you can edit the service. I mean, it's not advised to edit, but just for viewing purpose. Let's say service front-end. So, so this is the actual state currently like in the cluster. This is not the YAML file just we provided, but this is the actual state, right? So you can see the cluster IP, everything allocated, right? And also the type of the service is node port. That means in this particular host, and if you access that particular port, I can see this, see the service running. So I'll change this to load balancer because I have firewall rules which will not allow me to access, the random ports like 30,000 plus. Just for explanation purpose. So what I've just done is I just modified the service of front end, right? Previously it was node port. So as per the explanation, the node port we cannot, we will be able to access from that 30,000 plus port in the host. So it's host IP colon that port number we should be able to access. But right now I may not be able to access it because of the firewall, because only 80 and 443s are enabled. Now, so what I did is I just changed the type to load balancer because load balancer are public facing. By default, it assign a public facing. Now, if I already made a modification. Now, if I go and check the service details, describe service front end, you can see that it automatically assigned a load balancer, right? Now I can use this load balancer, DNS name to access this particular application, and it's available in port number 80. Right now, if I go back to my so the AECD, so it will take a little while before it get activated. AECD. Okay, it's in service. So this load balancer is automatically provisioned. Okay. We'll come back and check this URL in some time. By the time it will get activated. All right. So yeah. So I see some of the questions coming from the chat. So the load balancer who created it's Kubernetes take care of it. So there are different controllers, which is cloud specific, which will take care of assigning the load balancer. So there are different implementation. Like for example, if you here by default it's using the classic load balancer, not the other one. So but again we can customize it as well. We can pass the parameters. So there's something called annotation. So we can pass annotation to a service which is specific to a cloud vendor. Okay, so using which you can configure it. So it's doable, but it's kind of little advanced topic. So on a high level, the way it worked is like there are multiple implementation of this, right? So it is nothing to do with the COPS, rather it has to do something with the Kubernetes. So even if you configure the same thing using kubeadmin, kubeadm, individually, it works the same way, right? So if you give the type as load balancer, the Kubernetes automatically, the custom controller will automatically provision the load balancer and do the record stuff like the target groups and adding instances and etc. So that's automatically taken care. All right, so our application app up now. If we So this is a simple thing: is that guest book you can add something, and if you refresh it, it doesn't go off because it's coming from Redis. Right now we can try terminating the Redis port and see like whether it's still there. But thing is, like, if you try terminating the Redis port, it will automatically create a new instance because the replicas always watch and create a new instance if something is dead. So if you manually try to kill a port, it automatically create a new one. If you want to see that, kubectl get this list all the available ports. Yeah, I mean, we won't be able to even, because it's quite fast, that you won't be able to even see that happening. All right, so now let's go back to the slides. Yeah, so what we have seen so far is we created we created the ports, and using deployment, which contains the number of replicas required, as well as the container image and things like that, right? And then we have the service, and using service we can access the application, right? So we talk to the service, and service talk to the ports. So service is a virtual entity. It's not something like like a port where you can have a virtual Ethernet or something, but it's totally virtual. We'll talk about that during the network session. So service discovery. So Kubernetes support two types of service discovery. So by default, it support something called environment variable. So basically, it creates the environment variable for each service, and which will have its IP address. So if you want to look up based on the environment variable, we can do that, right? So, but that's not a reliable way of doing it, because you need to follow a certain order, right? So otherwise, the cases you won't be able to see that. That is one. And second is like the environment variables are defined within a node, right? So it will not create the same set of environment with all the nodes, right? So the reliable solution is DNS. So basically, it's an add-on, like we discussed earlier. So it's an add-on which you install with the cluster. So it will have DNS in all the nodes. So then what happens is, like, it modify the port in such a way that when the container start up, it automatically make the the service, the name server entry in the host file. So it now, the containers know that what is the name server, right? And it will have the the complete the names, in the sense like all the port names and service names. So whenever a client wanted to talk to a port, want to talk to another port, or a service want to talk to another service, it will resolve it to an IP address through the DNS. So it works like any other DNS server. It has the the records which we pass the name and then resolve into IP address. So in this typical example, this is how the service discovery based interaction works. Like, we have a client first register itself to the registry. In this case, it's a DNS server, right? And then if you want to talk to that, you first look up the registry and get the IP address and talk. So this is the implementation look like when you have a external service registry. But in terms of DNS based discovery, you're actually looking up the name in the DNS server and giving it the active IPs. So again, like, if you add the add-on, which is the core DNS, there are multiple add-ons available for DNS. So if you add one of those add-ons, then you don't have to worry about it. So it's available cluster-wide. So it's not just within the node, but again, like, the it gets resolved across the cluster. So now the interesting thing, the networking, right? So on a high level, there are three, three points that we need to consider before implementing the Kubernetes cluster networking. So when I say before we implementing, it's like before a vendor implement a network plugin. So there are multiple overlay networking solutions available in Kubernetes. So all the vendor has to follow these three instructions. So the first one is like pods are all able to communicate with one another without the need to NAT. So basically, that's why in Kubernetes, every pod has its own IP address. Unlike in the Docker Swarm, the IP addresses can be duplicate, meaning the IP addresses are unique only within a node. So you have two nodes in a Docker Swarm, then there can be duplication of IP address. But in Kubernetes, and that's why we do a lot of pod mapping in the Docker world. But in Kubernetes, every pod has a unique IP address, and each pod should be able to talk to other pod using its IP address, right? But yeah, the first point says is like all the pod should be able to talk to each other, and nodes are the machine, and the nodes again a pod in a node one should be able to talk to a pod in a different node. So that's the second point. Again, without using a NAT, right? And then the third point is the IP address that a pod see should be the IP address others see. Basically, everyone should have a unique IP address. Every pod should have a unique IP address. So these are the three primitives or three instructions that the network plugin or network overlay plugin vendors will take care. And there are multiple options available in Kubernetes which you can choose, and which sets up the complete network. So we are not talking about we have covered like two aspects of it, right, or three aspects of it. So one is like how to talk from between pod within the node, and second is like how to talk across different nodes, and the third one would be how to access these services from outside the cluster, right? So these are the four points. One is container to container networking, then port to port networking, port to service networking, and internet to service networking. So container to container networking is pretty straightforward, right? Because what is a port? A port has a shared network namespace, right? Which means it has the same IP address and the ports, right? So which means like a container in a port want to talk to another container in the same port, actually talk like a local host. You don't really need a network. So second is the port to port networking, right? So on a high level, so this is how it works. So the outer box that you see is the actual node, right? So it has the H0 or the network card, and you have the root network namespace in the host machine, right? Then there are different namespaces like port 1 network namespace, port 2 network namespace, like we discussed the initial slide. So we can create multiple namespaces, right? Like in Linux. These are the kernel features, and not so we have three namespaces. One is the root namespace where actual network card is plugged, right? And we have different network namespace for each port, right? Then we have something called web pair or virtual Ethernet. So the complete networking is kind of virtualized. So you can create a virtual Ethernet. So that's how you set up networking within VMs, for example, right? So we have virtual Ethernet. So you can create multiple virtual Ethernet. So and it is called virtual Ethernet pair. So why it is called a pair? Because one part of it is connected to the root network namespace, and other part is connected to the the target namespace. Let's say pod 1 namespace, right? So this is doable because like we said, a container, for example, can share namespaces. That's exactly what we have seen in the previous diagram, right? So we have two containers which is sharing the network namespaces. So they use a concept called post container to implement this web pair. So you have this pair. So that post container is spread across share the same network namespace of root namespace and the port. So now we have the virtual Ethernet connected to the port 1, right? And then we have the other end connected to the root network namespace. And in the root network namespace, we also have a bridge. So in the host system, I can create multiple the virtual Ethernet devices, and everything is connected to this particular bridge called this is called custom bridge. CBR stands for custom bridge. Now the communication works something like this, right? From port, if I'm sending a message to, let's say, port 2, so we know we are sending a message to a different IP address, right? So port 1 has an IP and port 2 has a different IP. So I'm sending a message to port 2 through the custom bridge, and bridge, the way it works is it broadcasts to all other connected devices. So and whoever owns that particular message will respond back, and then it caches, and next time when you try to do the same, it know whom to route, which device, which endpoint it should route to, right? So basically port send a message to bridge, and bridge will send to the port 2, right? So it's easy. So it's done through virtual Ethernet and bridge. Now we're talking about how do we communicate across different nodes. Even this we don't really have to know like how it actually internally works, because this changes is purely based on the implementation. So the multiple cloud vendors have their own implementation. There are different vendors provide overlay network. So overlay network is nothing but the virtual network that you define on top of a physical network. So this is like within the Kubernetes cluster, you can have an overlay network that's a totally virtual network which understands all the connected devices in that particular network, and it knows how to route to each endpoints. So on a high level, here port 1 wants to talk to, let's say, the port 4, which is a different node. So here it works the same way. It reads the bridge, but then bridge does not have a connected device, so it actually passes it to the root NS, the adapter. But then the thing is, there is some magic happens in between. So that's how using something called IP tables. So there are a few IP tables rules get fired up. That's how we identify the target the IP. So basically, what you can see on a high level is like a multiple node which is connected using some kind of mechanism within the cloud provider or your the local data center infrastructure. So you'll have a default gateway or router using which you connect two nodes. So and within the nodes or within the cluster, we have overlay network which will take care of how to route the packets like from one to another. And then we have the ingress controller. So we on a high level we test base how the ingress work, right? So if you have a load balancer mapped to service, then we need to have multiple load balancer. I mean, each service should have a load balancer. So ingress controller pretty much help you here. So basically, usually there's an Nginx ingress controller, and there's a separate open source project, and also there is one project from Nginx itself. The implementation is in Nginx Plus. It's a paid version. So based on different routes, it will be able to I mean, when you say route, the path, request path, it will be able to route to different services. And this implementation usually even the ingress controller will be will have a load balancer, though it is not a load type is not load balancer, rather it's an ingress, but still it will have a load balancer. And we have few more stuff, and before that, after that, we'll quickly go through and see like how to set up the cluster. So network policies. So on a high level, what network policy is like, we have multiple ports. Now it allow you a mechanism to define who can talk to whom, right? So if you wanted to, by default you can talk to all the ports, but then you can deny for all the communication and isolate the complete inter-port communications, or you can selectively do that. Like for example, in this particular use case, the port A can talk to Nginx, but then port B cannot talk to Nginx. So if you look at the network policy, this is the policy applied to Nginx. right? Because it is applied based on the label app nginx that you can see there. Now ingress the inside traffic from port selector only from the ports which has a matching label of app equal to foo, which is for port A. So basically, it targets. I mean, Nginx accept only the port A, traffic. So likewise, you can define, network policies across your application. And persistence. This is a concept which is slightly difficult to understand initially because because it does not work like, let's say, Docker, right? So, and the way it is set up like this is mainly because it has to be easily integrated with multiple cloud vendors. So every cloud vendor can have their own implementation. So you should be able to the plug and play, right? So that's the reason, one of the reason why there are multiple levels of abstraction when Kubernetes uses for defining persistence. So on a high level, these are the four options. Volumes. I wouldn't say these are the four options. These are the four things you should know. The volumes. So volumes are the shared volume, like in a pod. A pod can contain multiple containers, right? So you can define a volume, and then that volume, the life cycle of that particular volume will be tied to the life cycle of the pod. Let's assume you have two containers in a pod, and one of the container terminates. So then the pod automatically restart the container, right? So the volume doesn't goes off. The data doesn't goes off. So data will exist till the pod crash. Let's say you kill the pod, then you lose the data. So that's the first option, which is not very useful in most of the scenarios. Now the second option is persistent volume and persistent volume claim. So to understand on a high level, I quickly go to the second slide and come back. So this is on a high level process. Like for example, an infrastructure administrator will provision the required, the storage, like in different cloud or wherever it has to be. So that is called persistent volume, a piece of storage that the administrator provision, right, for the application to use. So that is the first step, right? Now, in the application, a developer will add a claim. First of all, a developer will define a claim for accessing that particular storage. Like for example, administrator, provision 100 GB SSD, right? Like in, let's say, AWS. Now the developer wants 5 GB of it. So basically, he will claim. So there is a resource named claim, using which he will make sure he gets 5 GB, right? Then third step is he need to reference that particular claim in the actual pod itself, so that when the pod actually start, he'll be able to make use of that volume. So we'll come back to that again in the YAML, so it will be easier to understand, a little more easier to understand. So as you mentioned, the pod volume, so persistent volume, it is the piece of storage that you provision in advance, and persistent volume claim is for requesting the storage from PV. Okay, and there are different types of storage. Like for example, different types of different cloud vendors have different storage classes. Like let's say EBS, like in AWS. Like there are many, so you can see the complete list in the help documentation. Now, let me quickly go back and show you the YAML file, which will be more easier to understand now. So what we have seen is like you have the persistent volume, right? So this is how, and it is again another, Kubernetes resource. Kind is persistent volume. You are defining a persistent volume. So this is not a classic example because here the volume is not a cloud volume. It is just, another, technically this directory, or this is actually storage within the node, right? So we said storage class name as manual, and then 10 GB is what required, and basically this 10 GB is in the node. Now persistent volume claim, right? So basically it refers to the persistent volume, which is class name is manual. So you can see the storage class is manual, and access mode, it requires read write once. So there are multiple access mode. So read write once meaning only one port should be able to read write to it. So there are different access modes, and also it requires 3 GB. So basically 10 GB is allocated here. It's looking for 3 GB. Now this claim, this another artifact or another resource within the Kubernetes, right? You can see the kindness persistent volume claim, and now this claim will be referred here in the actual port declaration. So you can see the name. Sorry, that's the container name. Yeah, so volume is actually the same level as a container. So a pod can contain containers as well as volume, right? So it's the same hierarchy, and you can have multiple volume. That's why you see the array. Now you can see it is referring the persistent volume claim. The claim name is nothing but task PV claim, which is the first, which is the second one, and also where it should be mounted. So it will be mounted within the container. So you can see the volume mount where it will be mounted. It is a little difficult to understand this, like at the first time, but most often we end up referring the template to implement this. So I'll see some templates which we do for setting up Mongo as well as Elasticsearch. Now this is the typical life cycle for given the storage. So you provision. There are two ways to provision: static and dynamic. When it's a static, like you saw in this diagram, an administrator has to manually provision and make it available like 10 GB in advance. So that is static. And in Kubernetes, if you enable dynamic provisioning, it automatically provision. If it did not find anything statically defined, then it automatically provision from the cloud. So wherever you run, it automatically provision. But for that, you need to explicitly enable that. So that is how you provision, and then you bind. So as you have seen the PVC to PV binding, then you mount the volume to the port for the using it. Then once the port die or you don't want to use that particular volume anymore, then you can reclaim and add that particular volume back to the pool so that others can use it. So when you say reclaim, there are three things: retain, delete, or recycle. Delete meaning like when the port die, it automatically delete it. So retain will keep it, and recycle is kind of same thing. Sorry, retain will keep it. Recycle meaning it actually delete the complete data uh, within the volume. So few more things need to talk about. Then after that, we'll show and we'll go through the current cluster setup. So the login architecture. Uh, So there are two things. People usually get confused with the logging architecture and monitoring architecture. So logging, we may, I mean, the most famous tag is like ELK, or now it's Elastic. But instead of Logstash, people tend to use Fluentd. It's getting more traction. So if you look at this, so you have two nodes, two worker nodes, right? So you have multiple ports running in each of these nodes, and these ports, writing logs. So it's available in the container logs. And what Fluentd does is, Fluentd is a daemon set, like it runs in all the nodes, one instance in all the nodes. So it actually pull the Docker logs and push it to the Elasticsearch, right? Push it to Elasticsearch. So basically, you have this daemon running in all the worker nodes, and then it pull the Docker logs and push it to Elasticsearch. So once it is available in Elasticsearch, then you can have the Kibana setup. That's the UI using which you can access it, right? So in terms of setting up the cluster, usually in production, you may not set up the Elasticsearch and Kibana, etc. within the worker node. Rather, you can have separate infrastructure node. Like when I say, for the redundancy, we can have multiple nodes. So that's why I've named it as infrastructure cluster. So it can be more than one node. So basically, you can keep all the infrastructure tooling outside the worker nodes. So, but in dev or non-production environment, you can have even Kibana, all of this running in one of these nodes. You don't have to set up separate cluster for that, right? So how would it look like and how to set it up? So here is a straightforward thing. So if you go to logging, so I'll share the Git repository. Just I started adding some details like yesterday and this morning. So it's in a very initial stage. So I'll be keep updating it like on a regular basis. So you can see the Elastic Stack, Fluentd, and config. So where is this YAML files coming from? So if we go to the Kubernetes project, so it has cluster and add-ons. Under that, you can look for Fluentd Elasticsearch. So this is the same thing, right? So basically, you have the Elasticsearch, you have the Fluentd, and you have Kibana. So you can see the Kibana is the UI, and Fluentd is the one which actually collect the logs and push to Elasticsearch. Elasticsearch has the database, right? It's a NoSQL kind of database, and you can cluster it. So in Elasticsearch, you can see the service and stateful sets are used for something like database. Now Fluentd have two. One is the config map. This we have not. So config map is a way to store key value pairs within the cluster. So all the configuration key value pair you can actually store within the cluster. You don't really need a new tooling. So that's another resource type in Kubernetes. And these are the YAML file which you execute, which you apply, then it automatically set up this complete thing like in your cluster. So, and one thing to note that you need a cloud storage. So that's why we have created a PVC and a storage class. So here storage class is nothing but AWS EBS, right? So basically what I've done is I've gone here and went to the volumes and I've created two volumes of 10 GB in two availability zones, right? Because nodes can be in any of the availability zones, and then uh, and then so this is the storage class, right? So and then the claim mentioning like I need 10 GB. I think it's also 10 GB. Yeah, it's defined as 10 GB. I need 10 GB of this storage class. So now where it is reference, you'll be able to, you can see that reference like in the Elasticsearch where modem claim reference of cloud SSD, right? Now once you have that, once you apply those two files, how do you apply? You just have to use your kubectl apply -f stands for file and give those file names. If you have all the files in single directory, you can also give dot. So basically the current directory, it will take everything. So once you apply, then all the services and ports will be running, right? So then you can get the endpoint details by querying the service, or you can also check the YAML file. Like for example, kubectl describe. Okay, before that, kubectl get service. Okay, I don't see it. I think it's in different namespace. All right, so I can see that. So this is a Kibana logging. So this is the service for the UI, right? Now, if I want to access this particular UI, you can see the details by querying it. So kubectl describe Kibana logging. Service. Okay, you want to see it because you need to pass the namespace. By default, it will only list things in the default namespace. All right, so now you can see the load balancer. So this is something I think I modified it. So usually, I mean, it was not port. I changed that to load balancer so that I can access from outside. So since I have this IP restriction, support restriction in my current setup, so this is how it looked like. So basically, I'm getting the same endpoint, right? So this is how it looked like. So all your logs are now in Elasticsearch, and you can define the new dashboard. This is something I quickly created, so I didn't create a dashboard, etc. But then you can play around, right? So that's about the logging. So this is actually for monitoring application logs, not the infrastructure logs. I mean, some of the infrastructure logs also flow in here, but the main intention is for troubleshooting the production application. Now, the monitoring architecture is for you know uh, managing the cluster, meaning like monitoring the cluster. So you want to see the resource utilization in all the the containers and all the nodes and etc etc. And also you can see the logs. So basically, it is for monitoring the cluster. Other is for monitoring the application. You can uh, kind of say that. So this is the architecture for Prometheus. So on a high level, uh, Prometheus and Grafana. So Grafana is the UI. So Prometheus has the agent running everywhere. It collects the metrics. There are multiple uh, places from Prometheus can collect the data, and there are multiple integration as well. But the whatever I have deployed is kind of straightforward, which I can take you through. And once you have the data, you can actually visualize through Grafana query Prometheus, and you can kind of visualize the data. And alert manager is for sending alerts. So if you want to create some production alerts based on some kind of filters, etc., from the logs, then you can do that through alerting. So alert manager is also part of Prometheus. So one way to set out all of these are like you can install them separately. Like for example, even in the previous case, we have the Kibana, we have the we have the Kibana, we have the Fluentd, and Elasticsearch. So you can configure them. I mean, set them up separately, and then you can connect them. So that's one way of doing it. And other way of doing it is like you can deploy already available package. So like in many other languages and platform, Kubernetes also have a package manager. So it is called Helm. So basically, we can package the complete Kubernetes application. When you say complete Kubernetes application, it can contain the deployment, it can handle service files and some config, etc., etc. So everything can be combined together and packaged and pushed to a repository. And then using the command line, using the helm, you can actually install that particular application. And the one cool feature would be you can roll back in a very nice fashion. For example, if you are applying the resource files for deployment separately, services separately, and some other configuration separately, etc. If you want to do a rollback, technically you need to actually change everything and then roll back. But it's not as good as like a single command line. So, but when you packaged using Helm, then you can easily roll it back. So again, I have documented that part how to set up. So basically, it's using Helm for setting up the Prometheus. So this is for installing the Helm library in your node. After that, you need to do a Helm init. So it has a daemon running in all the nodes called tiller, right? So this is required for setting up permission for it. And then after that, it's as easy. This is about just setting up your package manager Helm, right? Then after that, it's all about Helm install. Then you can give a name so that it is easy for you to roll back. You can just roll back by calling its name and namespacing. You can also, instead of putting everything to default namespace, all the infra stuff we can put into a different namespace so that it's separate. And then you can pass in the name of the application. So where is this coming from? Stable Prometheus operator. So basically, Helm has a concept called chart. Chart is nothing but this packaged application. So if you look for you'll see multiple flavor, but you can select exactly the same thing. Stable Prometheus. And there are different version. One with just the Prometheus, but not with the remaining stack, etc. So and once you are there, then you'll be able to just execute this particular command and install it. So basically, you set up the package manager, and then you execute this. Then you have the application installed. So if you want to see that working, you can go here. Again, the same procedure. If you want to see the node where it's running, because I given the namespaces monitoring. So kubectl get service and namespaces monitoring. So you can see the Grafana and all this Prometheus install. So what I'm looking for is Grafana, which is the UI. You can also see the alert manager install. So kubectl describe service and namespace monitoring. You'll be able to see the load balancer. Again, this is something I've modified. It was not code, but then I made it load balancer so that it's easy to access from outside and do a demo. So if you access it, then you'll see the dashboard, right? So this is the default dashboard. Then you can configure and create multiple dashboards and all of this, different types of metrics, right? Now if you look at here, you can see those additional load balancer which is spinned up automatically. Just take me a while. Okay, while it load. So we discussed about monitoring architecture, then service mesh. I would love to do a demonstration of service mesh, but lack of time as well as I did not create this test script. One thing I could possibly do is by next week I'll be populating the record script to spin it up here, like in the repository, as well as some kind of documentation so that people can follow. Um, okay, so what is a service mesh? So in the microservices world, like if you wanted to do the service discovery, or if you wanted to do fault tolerance, like for example the implementing the circuit breaker pattern, like for example I'm calling from service A to B and B is down, so A shouldn't be down just because of dependency is down. So instead of that it should fall back, right? Circuit should be open so that you don't make any call to A, so that I get the time to recover, and once it is recovered, then it will make the calls. And also things like if you wanted to check the multi API calls, like for example I'm calling from B to A to C, right? But then something is taking more time. So, but as a user, I'm getting total response time as more than what is anticipated, right? So then we want to know what is the time taken from B to A to C, etc., etc. So that is another use case. And one most important use case would be security. Like for example, inter microservices calls are not HTTPS, right? So you only have HTTPS till the gateway. So you have the certificate in the load balancer of the gateway where you terminate it, and after that it's all HTTP call, correct? So if you wanted to implement HTTPS in all the inter microservices call, let's say you have 50 microservices, it's going to be pain because for each of the server you need to set up the certificate, right? And also the application server has to now take care of even terminating this connection, right? So that's where you can use something like a service mesh. So it works very well with the Kubernetes and pods in specific. Why? Because a pod is a group of container, and we discussed initially about the concept of injecting a sidecar proxy. So the way it works is like for each pod is nothing but your microservice, and along with your the container, uh, we automatically inject a sidecar proxy. Basically, all the traffic towards the application will be routed to the proxy, and all the traffic outside from the pod will be routed to the proxy. So basically, then proxy can make intelligent decisions for routing, let's say latency based routing. So let's assume we have a call from servers B2C, but C have 10 instances, and proxy knows that which instance is faster because it makes all the calls, right? So proxy act as a data plane which collects the data, right? And then you have the control plane which actually makes the service mesh called pilot, mixer, citadel with respect to Istio. This is from Istio. So there are different service mesh, but Istio is the most famous one, which is a little more feature complete. So what pilot does? So pilot, the configure the proxies, and basically it will do the things like the circuit breaking and routing, etc., etc. And mixer is the one which will take care of. Okay, so pilot will let the packet move from A to B, right? Like routing decision, but then mixer is the one who handle when it's actually being routed, like the policy. Like for example, you want to restrict communication from B to A, so you can on the fly restrict that through a policy. So things like that. And Citadel takes care of the certificates. And this is very easy to implement. Like it's not that difficult. So basically, the sidecar proxy injection happens automatically. There are multiple ways you can inject it. You can explicitly and implicitly, inject it. Like for example, when you apply a pod, apply a deployment, it automatically update that particular thing with the proxy configuration. That is one way. And second is like using a command line, you can actually update the deployment script. Like for example, the YAML file, which automatically add the proxy section, and then you apply that particular thing to the cluster. So there are multiple ways you can do that. Yeah, and needless to say, there are tools like Jaeger, etc., which is kind of integrated with the solution, which will take care of the kind of latency check, right? Now we talk about the reference architecture, and we have two more slides to cover. So now that we have seen the Kubernetes like in a very high level, so how does it how we can use that for implementing something like a microservice platform, right? So when I say microservice platform, what I'm talking about, the developers just focus on their code, building that particular microservices, and the CI/CD when it merged to a certain branch or pass a certain gate, it should automatically deploy, make all the other configuration by its own. They shouldn't be worried about infrastructure like the service discovery and the circuit breaking or making some changes in the IP gateway, etc., etc. So everything should happen within the platform. So if you look at now, in this reference architecture, the bottom layer infrastructure is totally automatable, right? So you can define something like CloudFormation template for compute, network, storage, and security, etc., and run it over the CloudFormation will spin up the complete cluster. That's exactly what happens when you do, when you run the COPS for setting up the cluster. So we can automate, and different cloud providers have different ways to do it. It's about declaring them like in a YAML file and then running there the engine, and then which spin up the complete infrastructure. Now the container platform we have, I have not shown you, but then spinning up the complete the container platform, which is the Kubernetes, it's pretty easy. So with few command lines as well as some of the section we can represent in a YAML file, we can spin up the complete container platform. And then service mesh, it's about again another set of YAML files that makes a service mesh. So YAML file will, when I say YAML file, it is the deployment and services, right? With deployment, which define the ports, and inside the port you have the Docker container or image of those applications running, right? So basically, all of this can be spin up like in kind of click of a button, right? And then all the solution is integrated with, if you see the left side, you have the monitoring, different levels of monitoring. You can say the application logs, then the cluster metrics and health and things like that. So as you have seen, with few lines of command lines, so we actually split up. We are actually kind of running the whole system, right? And right side you talk about security. And some of the security, most part of it is scriptable, like you see all the in blue, but some of the security, require code level, changes. So And also, if you want to deploy the core services, like for example, if you want to deploy a Mongo or MySQL or in a rule engine or a workflow, etc., you can have a standard template defined for them. So you don't really have to do it again and again. So basically, when you have a platform something like this, the developer will not have to think about the complete infrastructure complexity. So one of the main complexity or the complexity in microservices based architecture is operational complexity. And the another side of it is like if you are able to design the microservices well by splitting up using proper bounded context, etc., then rest of it is actually simpler, right? Because developer has to deal with less line of code and the smaller functionality. So that part is actually easy. But what the complexity is about, how to run and in a cluster and with all these toolings and all this ecosystem. So but as you see in some part of it, I mean, spinning up something like this is pretty straightforward, and most of the tooling around it have matured a lot. So it is not that hard like before, where there are lots of internals you need to know for setting up a Kubernetes cluster. And there are already platforms available, as you may know, based on this, like especially Kubernetes. So one of them is OpenShift, and also you can come up with your own because it's all based on the OKD or OpenShift community distribution project, right? So based on that, you can also come up with your own version of the platform. But on a high level, it's a complete platform which integrates with the CI/CD and the uh, the the code. So developer commits something to the code base, it triggers CI/CD, and then it integrates with the system. It runs into the system, and it has a complete end-to-end infrastructure to do that. And but one of the drawback for using something like OpenShift is like it's kind of opinionated framework where you need to pick and there's no option like you can choose for most of the cases, like it is that decision is already made by OpenShift. So even if you want to create something which is loosely coupled, and if you want to choose your own tool set, etc., it's quite easy to build using all of that you have seen right now. And last but least, I've just kept one slide uh, to talk about some of the interesting projects like which is happening within the Cloud Native Computing Foundation. So if you go to CNCF, there are a lot of projects which is graduated, and some are adopted recently, etc. So this is some of them. I mean, not everything, but CNCF will be a good place where you can due to some reason it's taking time, right? So you can see all these new projects. So whenever new one comes up, when they adopt, they add this to the list. So there are a lot of projects in incubating, but only these many projects are graduated. So which include the Kubernetes obviously and Prometheus. So that's about it. If I am able to access AWS again, maybe I can quickly show you how to create a cluster. Looks like it's pretty slow. Yeah, so uh, let me take you through the script. And so in the repo, there is a folder named setup cluster. There are different ways to set up Minikube. I have not placed anything. So corps and kubeadmin. So corps is pretty easy. So these are the steps you need to do. So first install corps. So either you can install, I usually do all the experiments in cloud itself, which means, set up a host in the default network, default VPC, and then everything is based on this. So install corps, and then install kubectl, and install AWS CLI. Install AWS CLI if you are not using, AWS image. So if you're using AWS AMI, then you don't really need CLI because it's baked in. Then configure these permissions. So basically, you need to create a group and add some permission policy to that particular group, so that corps have this permission to automatically create those resources. Like for example, you can see give EC2 full access, Amazon Route 53 full access. So all of these are required for it to configure itself, right? Now again, like the way I would suggest is, rather than running this script, this part of the script, you create a role, and to that role you give all this permission, and then attach that particular role to the EC2 instance where you are running the scripts. And if you are running it from your local machine, obviously you may not be able to do that. Then this is the way to go, right? And if you are doing like this in the CLI, you're creating all this, then you need to set the AWS key ID and secret key as an environment variable that is required. So that is for cops to talk to AWS and do this using this credential. So if you are giving a role within the AWS instance, then you don't have to do it, but otherwise you have to do it. These two steps needs to be done. Then you need to provision AWS S3 for storing the state. So once you do that, you need to create a environment variable with the name of the cluster that you want to do. I mean, it should be something unique, and then name of the S3. So two different variable. Then after that, you can create your cluster. Okay, so this line is just to check what are the availability zone where you're working on, so that you can pass different availability zone here, right? So that's not required, so you can just create a cluster. So when you say create the cluster, it does not create the cluster, but it only actually build all the configuration. Then you'll get into a security issue because when you want to build a cluster, so inter-node communication, trust communication, you need the public-private key. So basically, you have to execute this. So you'll create that key, and then you can pretty much run corps update cluster, and with the cluster name, which is already part of the environment variable. So it actually spin up. So this is the time. It actually spin up the complete infrastructure. Okay, so which means you will be charged. You may be charged, right? Okay, the cluster, AWS is back. So if you look at what it created, so basically I've selected for one node, one master, and one worker node. But by default, I think they set for 3 and 2, but you can modify it by running corps edit. Okay. In fact, we can actually run it now to see the cluster. Okay. It's missing in the session. So I added it back. Corps validate cluster. All right, so I can see that one master and one node, right? Now, how do you modify it, right? So if you wanted to modify it, you can do this corps edit. So we see the maximum size and minimum size, right? So there you can actually go and modify. All right, and last but not least, if you want to delete the complete cluster, it's easy. So it's about corps delete cluster name. So if I do that, it's going to delete all the resources that automatically provision as part of building the cluster. So you'll see everything deleted except the passion host, which I manually created for talking. So one thing I will just show you about the IAM role which I've created. So you see the role, and corps admin is the role name. If you look at, so it has all the policies to care for this. And after that, pretty much you go here and associate that particular role with that particular instance. So that's why it gets right. So we don't have to Yeah, you don't have to manually create a group and declare environment variable with the credentials, etc. And one more thing it does, um, which is the auto scaling groups. So yeah, so how to make it kind of always available? Nodes are always available, right? So you create auto scaling group, and you set like I need 2 instances, etc., right? So I mean, which we have taken through, on one of the webinar previously. So all of these are done by cops like magic. So you don't really have to spend any time setting up a cluster, but then uh, uh, the cops does that. But somehow, I mean, for setting up production environment, I may be skeptical about this because I would like to, create the cloud formation, different templates myself, and then run it rather than cops automatically creating it. Because in that way, we have full control. Even otherwise, you can do some level of customization, but not to the extent that you may need. So now let's try to delete the cluster. So now it's killing the cluster. This may take some time. Then after that, if you refresh, you should see all of your, AWS is wiped out. All right, I think that's about today's session. I think I've taken kind of 2 hours. If you have any questions.
This conference will now be recorded.